Hello everyone, welcome to this SWAM-NPTEL online course on space environment and its effects on orbital spacecraft. So, in this module we are discussing the plasma environment and its effects on orbital spacecraft. And as we discussed, one of the most significant effect of this plasma environment on spacecraft is the spacecraft charging. Because of this charged spacecraft, there is the probability of a lot of anomalies. So, these anomalies we will be discussing, but these days we are discussing the physics, that is how a spacecraft get charged by using the plasma physics, that is the probe theory, and we discuss the Langmuir probe and the current collection, and we will continue with the same topic. So, we discussed the different types of the current collection in spacecraft, that is the primary currents because of the ambient electrons and then the ambient the ions, then the secondary emissions for due to the incoming energetic electrons or it can be the ions. Then we have seen the secondary emission because of the back, it is not emission, it is a component because of the back scattering. Then we have considered the photo emission, and now we will the same topic will continue, and we will see how we can get the current valence equation, and if we can form that equation from that current that is the valence equation, we will be able to compute what is the spacecraft potential or spacecraft built up potential. So, in the last session we were discussing that is the secondary emission of the electrons, and we said that there is a term, it is called the secondary emission yield. As well as when we are discussing the backscattered emission, we defined a term that is called the backscattered, that is the emission yield. So, this is the SUI and BUI, these are the statistical terms, and these are very important when I need to calculate the current components because of these two types of the plasma fluxes. So, as I said these quantities SUI and BUI, they are in order to know what is that coefficient. So, the material testings are done. So, when you have the data, you can form the empirical formula. So, there are a lot many empirical formulas are there, it was done by various researchers. We will just as a a representative case, we will put the two formula, one for SUI and other for the BUI. So, what I am going to discuss, this is the Sanders and Inouye SCY formula. So, this is the formula. So, here you see you can find the distribution or the secondary emission yield, this is SUI. If you know this coefficients that is ABC, if you know the ABC, you will be able to plot this delta E as a function of the energy, as a function of the energy of the plasma species. So, you see where A is given in terms of the E max. So, E max says what is E max, we will see it right now. So, E max is basically it is that energy at which you have the maximum SUI. Then the B again it is you can find if you know the EMX, then C you can find if you know the delta MX. So, these are the things we find from the experiments. So, whatever I was saying. So, this is the Emax. So, corresponding to the Emax you will have this delta max, that is the maximum SUI. So, once you have this for this empirical formula, or it is something like getting a cup fitting, or from the experimental data, you can form this type of formula with which this it can be this can be used to compute what is the energy and what is the delta or the SUI corresponding to a particular energy. So, I can I can do it at any energy, what is the delta E. So, this thing already we discussed, this curve already we discussed, what is E 1, what is E 2 and why it it goes it is monotonically decreasing. So, why it happens, all those things we discussed in the last session. So, there is another the other formula for the empirical formula for the BUI. So, this is given by Prokopenko and the Laframboise BUI formula. So, this is given by this. So, here again if you have the data data set, then you can find this coefficients, the unknown coefficients A, B and C to find or to plot what is the value of eta for a corresponding to a particular energy level. So, this A, B, C are the material dependent. So, you need to do that is you need a chamber where you can test the material, and when you get the data from using those data, this you can the A, B, C can be found out. So, there are many this formula for the SUI and BUI, it is published getting published time to time, and whenever this thing started for the last few decades, when people they came to know about the spacecraft charging and its effects, and when the spacecraft research started. So, from that time onwards these formulas are available, its modification, then updation, and whatever is it again it depends on how you are getting it. So, it is obtained from the careful measurements and the better the data fitting and how you train the data. So, all those things it is all the techniques are also getting evolved. So, you can have a better model. Those works which were done before, which were they did not take into the consideration of this material property, especially the surface conditions such as surface smoothness, contamination, cleanliness, then scrubbing, temperature. So, whatever the recent work, the recent the curves for or the recent model for SUI and BUI, that shows that it depends on these parameters also. Okay. So, now this is all about the secondary emission and the backscattered the species. Now, we will discuss about the photoelectron current, that is photoelectron the fluxes. So, you already know how this the photoelectric effect happens. Whenever you are having the energetic photon, and then photon can give rise to they can take out the electron, they can impart sufficient energy. So, that the electrons are taken out making a positive ion in the spacecraft surface. So, these things already we discussed, but what is the equation? So, here it is the similar type, the type of equations used for the secondary and the backscattered electron fluxes. Similar thing is, and the parameters like secondary electron yield and backscattered electron yield. So, this thing a similar formula is used. So, what is used here? This is the formula used as it was used earlier. Here this Fs omega, this is the incoming solar photon flux, or you can say it is like the distribution function. So, it is per unit area per second per unit photon energy. So, here this omega term it is used for the photon energy, like there we used it E, but here we are using it omega, and Y omega is the photoelectron yield. So, this is again it is per unit incident photon of energy omega at normal incidence. So, here it is the normal incidence is considered. The way it was I discussed, the way it was done for this AC and BUI. Similarly, here also it is not arbitrary incidence angle is not considered. So, these are all the types of the currents, starting from the primary currents, then the secondary currents, then backscattered current, photo emission. Now, spacecraft itself also can generate the plasma fluxes, or it can modify it. So, whatever we discussed till now, these are all because of the ambient, this is orbit dependent, these are all this governed by the orbital conditions, but here what we are going to discuss, this is because of the spacecraft itself. So, it can generate or it can influence the plasma fluxes, okay, through various mechanisms. So, a few of them we will discuss now. So, one is the exhaust from the plasma thrusters. So, it can form high temperature plume. So, already you know that is the onboard thrusters are used for the attitude and the orbit control system. You need to suppose you want to raise the orbit or you want to maneuver. So, the thrusters are needed. So, generally the chemical thrusters are used, but because of their higher efficiency and higher the longer period you can use, the electric thrusters or the plasma thrusters are very it is getting popular, it is getting extensively being used. So, there it can, when it is this plasma, the charged particles are getting exhausted. So, that will influence or that will go to the environment, and so this will contribute to the plasma environment. So, this is a self generated or the induced plasma by the spacecraft. Then in the spacecrafts, there are the types of spacecrafts where very high power is needed, as for example, high throughput satellite or very high throughput satellites. So, there the power requirement is very high. So, there there can have the arcing and all those phenomena, and they can also emit the charged particles. Again it is that all these things are dependent on the spacecraft. So, it is spacecraft limited or it is the induced the charges by the spacecraft itself. Then as we have seen in the neutral environment, that spacecraft can also induce the neutral particles through outgassing. So, in vacuum the outgassing happens. So, those outgassed particles, when it interacts with or when it gets impacted by very high energy, it can be proton or even it can be electron. So, those high energy impacts, or there can be the high and the radiation also. So, those radiation as well as the high energy the impacts of the charged particles can make these outgassed materials to ionize. So, this again the charge exchange will happen, and it is another form of that, it is the induced plasma which is generated by the spacecraft itself. Then when the spacecraft is orbiting to space, so it disturbs the surrounding plasma. So, what is happening? It creates a weak region. So, weak region means it is opposite to the REM side. So, what is happen because of this the plasma density will vary. In the weak region the plasma density will be the lesser. So, what it can do, this weak, it can lead to a reduced plasma density, and which is an altered plasma fluxes in the spacecraft wake. Okay. So, this can also give rise to the problems because of these changes or because of this shock waves. The characteristics of this wake, it depends on factors such as the spacecraft speed, and then ambient plasma density and the spacecraft's charging state. Okay. Now, we will discuss we have now seen the different current components. Now, what is the balance here? So, if you remember, just I was discussing the charging of a capacitor. When a capacitor is getting charged, or the best example I gave, that is filling up at the top, when the incoming you are filling it, so the level is increasing. So, whenever the charged particles are getting impinged, the spacecraft is the potential gets the potential will increase. So, at that time the Kirchhoff's law, that is the ingoing and outgoing thing, will not balance each other. So, you can have a net current here. So, what do I mean by the current balance? Current balance means when all the ingoing and balances the outgoing current fluxes. So, now we have the many components we will do, but first what we will do, we will take the simple example, we will consider just this receiving current I, that is the current or the flux because of the electrons and the ions. So, this already we discussed this, we are considering a spherical spacecraft. So, there is the incoming flux and there is outgoing flux. So, electron is outgoing and the electrons are the ions are coming. So, this is forming something is coming and something is going. So, when this rate will balance each other, the spacecraft will attain equilibrium potential, and at that time the total current will be 0. Okay. So, at equilibrium the potential phi will be determined by the sum of the currents, sum of the all currents which balances each other. So, this is the thing. So, I should use here a minus, so minus sign I use, because it is to show that one is outgoing and the other one is the incoming. So, this is nothing but the Kirchhoff's current law, and this already I said, that is we explained through this, that is, so you are, so this is incoming current. So, you can consider the plasma flux and the phi is the potential. So, whenever the balance is not there, so what will have, whenever you are pouring the water, so this phi will increase, but when you make an outlet and if you can balance this incoming and the outcoming the fluxes, so this phi will remain constant. Okay. So, this is already I said about the Kirchhoff's current law. So, I can assume the spacecraft will try to explain, that is, we will consider the spacecraft itself is like a circuit or as a junction that will come at the later stage when we will try to explain the equivalent circuit and how to calculate the currents and the the potential by the circuit theory. So, now we will consider the whatever the current components we considered, the different the secondary emission, backscattered electrons, or all those things we will consider now. Okay. So, in the spacecraft charging, the balance between the incoming and outgoing fluxes, that this ensures that the net current to this spacecraft is 0. Of course, during the charging this thing will not be 0, that we will have a net current. Okay. So, when the current is 0, then this the whatever the potential it requires, this is a built up potential during the electrostatic equilibrium. And this balance, it involves the several components of plasma currents and each contributing to the spacecraft's potential. Okay. So, with this illustration I discussed all those type of the currents. Okay. So, the last sentence, it is just a repetition, I am telling it again and again, that is what is the mechanism. The spacecraft gets charged negatively and then it repels the electrons. So, electrons becomes a outgoing species and it attracts the positive ions. So, it becomes a the incoming species. Now, we will consider all the components to write down the equation, that is the current balance equation. So, at equilibrium all currents sum to 0. You remember this, at equilibrium means when it is charged to a stable potential. When it is getting charged, that net there will be a net current, that net current is not 0. So, this if I consider the phi s, it is the spacecraft potential, then I can write the I net is equal to. So, these are the different current components or whatever we have already discussed. So, what is I phi s? I phi s is the primary electron current, then this is the primary ion current, then this is the secondary, when I am writing SE, this is secondary electron current due to the primary electron fluxes, and as I, this secondary electron current due to the primary ion fluxes. Then when I am writing BE, BE means it is the back scattered electron, and then PH means it is the photoelectron current. So, you see here this is nothing but this is the Kirchhoff's current law. Okay. So, this illustration also I showed you, it is the same whatever I showed in this earlier slide. So, what I was telling during the charging we will have some I net, that I will come later on, that is how I can get the the time varying, how the potential is rising, that thing we will be able to find. So, I net is not equal to during the charging of the spacecraft, during the charging of the spacecraft. Okay. So, now we will see that is how we can find the all this current components, all thing, because we need to have a mathematical modeling. So, this is very simple, this is all of us we know, that is if I have this, if I know this charged particle velocity, if I know this what is there in its density, and the if I know its charge, then I can find the current density. This is the formula, but here the V will have some it will have some velocity distribution, it will have the velocity distribution, and in the thermal equilibrium case, considering a isothermal or it is condition T, we can express this is by the V by that is a probability distribution function, that is the Maxwell and Boltzmann's distribution function. So, I can write this expression like this, where this f will contain this n. So, if you remember this formula, I have given it a number of times, I will put it here also. So, then I can write in the spherical coordinate or the polar coordinate system like this, and this already this velocity distribution, that already we know, we discussed it in the last classes, where m is the electron mass, k is the Boltzmann's constant, and T is the electron temperature. Okay. So, this is the same. Now, since the electrons are here we are putting it in V. So, this again I told you earlier. So, I can write it this expression in terms of energy, but just by replacing m v square by 2 by E. So, this gives me the energy distribution. Okay. So, I can write my the current density by using this equation, and finally, I can write the balance, if I just taking the outgoing and incoming electron fluxes, considering the the backscattered, and of course, here we have not considered the photon, that is the photoelectric current. So, I can write it like that, and then if I considering the normal incidence, and if I consider that, then I can write this equation will become like that, because this term, the angle term will go away. So, in that I can write it this expression like that. Now, we will shortly tell you that is it is a closed form expression, you need to derive it using those whatever the formulae I gave you. So, the incident current density we can find it by this equation. So, here all these parameters, m is the electron mass, and this is the distribution function, Maxwell function we will use it, whatever I have given in the last slide. And what is E dash? E dash is the energy of the electron on the spacecraft surface expressed in this way. Now, the same thing if I do it for this ion thing, then this sign will just change, and you have seen it, we have discussed it for the other species, it will shift on the other side. So, this thing already we discussed. So, secondary electron current density due to electron impact. So, here I need to put this SE, that is secondary electron emission yield. So, otherwise it is the same formula we are using it here. So, if I know that the secondary electron yield, then I should be able to calculate the what is the flux density because of the, or you can say it current density because of the secondary emission, and we are considering it here the primary is as the electron. Similarly, you can find it for if the primary thing is the ion or energetic ion, what is the secondary emission using the so E will be replaced by I only. Similarly, I can write the backscattered, the expression for the backscattered current density, and here I will use this is that the BEY, that is the backscattered electron yield, and otherwise it is the same. So, now let us discuss the photo current density. This is the one of the type of, that is the plasma or this is the the electron, it is generated because of the photon, that is the solar photon. So, this already we discussed. So, the photocurrent density, the JPH, that is independent of electron or ion impact, that is given by this formula. So, this is the formula. So, the first part this is valid when the potential is negative, and this is when the potential is the positive, because here both the cases will come whenever the electron is emitted, there will be a positive the ion. So, that way spacecraft can get positively charged also here. So, here this APH is the photo constant of the material expressed in ampere per centimeter square, and phi is this spacecraft surface to space potential, it is expressed in volts, and this T here it is the photoelectron temperature. If I want to calculate the built up potential of the spacecraft bodies, so what I need to do, I will consider here that is this I net is equal to J net. What is I net here? I net is this when the spacecraft is getting the charge, it is in the transition region, it has not reached to the equilibrium state. So, the I net is here is during the transient period when the spacecraft is developing the potential. So, where from I can get the I net? I net I can get from that Kirchhoff's whatever they applied with the Kirchhoff's current law. So, where so I can get the current by multiplying the the density, that is the current density. So, it is the A n body is the area of the surface of the nth body. We will see that what is nth body, why I am calling it nth body. And then I can write this I net. So, I can write it like this way. So, it is I can write the total charge is equal to C into V. Okay. So, if I now differentiate it, so dq by dt, it will be C dV by dt. So, dV by dt will be, and this is your current, dq by dt is the current. So, I can write it like that. So, so you see what I if I want to find this spacecraft potential, then I need to calculate the potential, and I can use this. So, I can first calculate the I net. Of course, all these things need to be done numerically, and then you will be able to calculate this. So, I will end it here, and again in the next session we will continue from here. That is, we will take a practical example and we will try to I will show you that is how I can calculate this the potential developed, or how this a temporal variation of the potential when I know this what is the all the current components, I can compute the a finite net current from all those current components, then it is possible to do it. And let me conclude here. Thank you very much.